Hearing 4. Okay, so we ended last class talking about circuits. Okay? So remember the simplest type of circuit that we talked about was a series circuit. All right? And remember series, just like it says, series when you have one resistor just back to back with another one. If we want to find the equivalent or total resistance of this circuit, what do we have to do? Yeah, add them all together. Okay? So in this case, 2 plus 1 plus 3, the equivalent resistance of this circuit is 6 ohms. Okay? Now, one of the disadvantages we said to a circuit like this is that if we take out one light bulb, if we take out one resistor, the whole thing goes down. Okay? Because if we take out one of these, we basically opened up the circuit, meaning that electricity no longer has a path to travel anymore. Okay? And that's why, for the most part, we use parallel circuits for a lot of things. Okay? Parallel circuits, if one light bulb goes out, there's still a path for all these. Now, the only thing more complex about this is the fact that, well, let me get to it. Okay? If we have a parallel circuit, let's say like this with two resistors, okay? We can't just add up the resistance values anymore. We have to take the inverse. Okay? So for a resistor like this, we have a 2 ohm and let's say, I don't know, a 3 ohm. Okay? We have to say that the equivalent resistance here is equal to 1 over that first resistor plus 1 over that second resistor. Now, we can just add these together and then take the inverse, but really what I'd like you guys to try to start doing is just use that lowest common denominator and do it by hand first as a way to check yourself. Okay? So in this case, what's our lowest common denominator? 6. So we have 3 over 6 ohms plus 2 over 6 ohms. It's going to be 5 over 6 ohms. And if we do this by hand, all right, we can also check ourselves and say, well, I know my resistance should be in ohms, not something over ohms. So this is definitely still equal to 1 over our equivalent. So if I flip that over, then I have 6 over 5 ohms, or about 1.2 ohms. The other thing that's always going to be true of systems like this too is the fact that our resistance is always going to be lower than our lowest value. Okay? So we're making it easier for this electricity to travel by adding this 3 ohm up here. Okay? So even though this is higher than 2 ohm, our end result is still going to be lower than our lowest, in this case 2 ohms. So we know we're on the right track. All right. So this is where we stopped last week. But what we need to talk about now is the fact that not all of these systems are just series or parallel. Most systems are some combination of the two. Okay? And when we have some combination of the two, we have to look and say, okay, what is in series with what and what's parallel to what? Okay? Let's take this for example. Say 2 ohm, 3 ohm, and a 9 ohm. Okay? What's in parallel here? The 3 and the 9. Okay? So 3 ohm here and the 9 ohm here are parallel. This 2 ohm is in series with this whole thing. So the first step we have to do here is we have to say what is the equivalent resistance of this part. Okay? What? No, because remember we have to take the inverse. Okay? But if we treat them as separate parts, then it won't be that bad. Okay? Because this is just doing the same thing we did before. Okay? Well, we can do that real quickly. 1 over our equivalent is equal to 1 over 3 ohms plus 1 over 9 ohms. Yeah, so 9 is our lowest common denominator. Good. Okay. So when we add these all up, we get 4 over 9 ohms. But once again, we have to take the inverse, so it's 9 over 4 ohms. So about 2.25 ohms. So what this means is that we could actually redraw this circle. Okay? We could redraw this and just say this is the same as having a 2 ohm resistor in series with a 2.25 ohm resistor.
I'm sorry. Well, how did you get 3 over 9 now?
Okay. Because we're saying we have to find our lowest common denominator.
Right.
Okay? So for us, that's going to be 9. Okay? So in order to get this bottom part to be 9, we have to multiply it by 3, right? And so if we do the same thing to the top, then we get 3 over 9. And remember, too, I mean, if you forget one way, you can always check it with the other way. Because if we just added 1/3 plus 1/9 and then took the inverse, we would still get 2.25. Okay? So in the end, what we get is a 2 ohm and a 2.25 ohm here. All right? And so what do we do here? Just add them together. So we have 2 ohms plus 2.25, so 4.25 ohms.
Just give me one test.
Yeah. Well, here, why don't you guys try one of these? Okay. Okay. Let's say we have a 5 ohm up here, okay, a 3 ohm, and a 7 ohm. Okay. See if you can tell me what's the equivalent resistance of this circuit.
Don't say it out loud.
Don't. Okay. Yeah, take a couple minutes, and if it is easy for you, help your neighbor. Are you stuck?
Yeah, we're both started off, but I don't know how to start it off.
Okay. Well, can someone say where would the easiest place to start this off be? Yeah. Because these are in series with each other. So the first thing we can do is add those together. Today is the 11th. What'd you guys get for this? 3.3 sounds about right. Because remember, once we're done adding these together, and you don't have to do this, all right, but we can just redraw this as a parallel with a 10 ohm and a 5 ohm. Okay? And so once we do that, to set that up, just 1 over our equivalent is equal to 1 over 5 plus 1 over 10. 1 over 5 is the same thing as 2 over 10. So we end up getting 3 over 10 ohms. If we flip that, we get 10 over 3 ohms. So about 3.3. Okay. Good. So any questions about circuits? All right. So we have a couple new things to talk about in addition to circuits. And then I promise we'll have plenty of time to review. Okay? But something we should have talked about a lot earlier probably, all right, is really a couple safety features. Okay? Now, this test in general and really this chapter is really going to be a lot more conceptual based. This means we're going to have a lot of concepts that I hope you'll be able to explain to me in a sentence or two. Okay, because remember the last test was maybe 2/3 equation-based questions and maybe 1/3 conceptual. This one will be a little closer to half and half. Okay, so that means that you should be able to explain what the difference is, what a couple safety features are. All right, you should be able to explain what a circuit is. Okay, and really the only two of the most important safety features we're going to talk about are fuses and circuit breakers. Now, luckily for us, fuses and circuit breakers aren't that complex. Okay? You have circuit breakers in your house or apartment or wherever. You have fuses in a ton of other places. Okay? But before we get into that, let's see how much we do know. Okay, I have a couple demonstrations today. This is just a D battery. Okay? So I connect one end of the D battery here. And let's say I connect the other end. What's going to happen? It's going to be a short. What else is going to happen to this battery? It's going to get really hot. Okay? And really, that's true of a lot of electrical systems, right? Okay? I mean, even if you think about something as simple as maybe like a laptop. You have a laptop on for a couple hours and on your lap. What's going to happen? It's going to get hot. It's going to get pretty hot. Okay? We're just going to speed that up if I shorten this out. Okay? Because remember, electricity is really just a bunch of energy. Okay? And so no energy transfer is perfect. And what's always going to happen is there's always going to be some amount of heat. So if I just short this out, if I just create a path for these electrons to travel, they're just going to keep moving, constantly getting hotter and hotter and hotter until eventually something bad's going to happen. Okay? This is why we have things like fuses and circuit breakers. Okay? A fuse is a relatively simple device, all right, that just has a tiny little ribbon in it that's designed to fail at a certain temperature. So if this thing gets too hot, basically this ribbon in the middle is just going to burn out. And what do you think happens if this ribbon burns out? Okay, there we go. We've opened up the circuit. We don't have a path for these electrons to travel anymore, so that electricity stopped. Now, what do you think a disadvantage to a fuse is? You got to replace it. Okay? So every time this goes out, there's no fixing this. We just have to replace it. So that's why in your houses, you mainly have circuit breakers. Circuit breakers work on pretty much the same principle. If there's a short, this little strip here gets hot and bends. Okay? That's it. It bends, opening up a contact, opening up the circuit. So you don't have electricity flowing through here anymore. And what do you do when your circuit breaker trips? You flip it back. Okay? You unplug that, I don't know, extra microwave you had going, and you flip your switch back. Okay? So the circuit breaker is reversible. You don't have to replace anything. But now at the same time, where do you still see fuses? Cars, all right, big electrical appliances, really, all right, something where it's not practical to have a circuit breaker. Okay? but both work on the same principle. If there's a short, if there's too much current going through there, all right, that heat's going to cause them both to fail, all right, and open up a circuit. Now, the other common safety feature that's a little bit different, that's in most electrical things, okay, is some sort of grounding wire. Okay? Because something that all electricity is going to do is always going to take the path of least resistance. Okay? This is exactly why you don't want to stand under a tree in a lightning storm. Why don't you want to stand under a tree in a lightning storm? Okay? Because that tree's taller, okay? And so when that lightning strikes, it's more likely to hit that tree than the open ground. Okay? That's why big buildings have lightning rods on the top. All right? So they provide a path for that lightning to travel, all right, that isn't through the building. This is the same way you don't stand on your metal drain while you're taking a shower during a thunderstorm. You guys ever heard that? No? Okay, well now I've put some fear into you guys, all right? Let's think about this for a second. If lightning hits your house, where's it easiest for that lightning to travel through? Metal, okay? Through your metal wiring in your house, all right? Any metal pipes you have, all right? Basically anything metal is going to be easier to travel through. So if you're standing on that drain, suddenly you're connected to something that's a lot easier for that metal to travel through, all right? So don't do that, okay? And this is also why you're safe in your car in a lightning storm, okay? Because what's your car made out of? Metal and plastic, right? So it's a lot easier for that lightning to travel through the metal of your car than it is through you.
Same thing applies, like when people tell you you're not supposed to talk on the house phone while it's like a thunderstorm, lightning outside.
Yes, yeah. Because, and the same way, I mean, it's unlikely your house is going to get struck by lightning, but if your house does get struck by lightning, it's going to be a lot easier for that lightning to travel through that phone line than it is through, I don't know, the wood in your house, you know, or insulation or something like that. Okay? And so this is why most things are built with this grounding wire in there. So if we imagine this situation without a dedicated ground and a drill here and there's a short, okay, suddenly you become the easiest way for that electricity to travel through. But if you do have that ground plugged in and there's a short, something breaks, okay, now you've provided this alternate path for that electricity to travel to the ground. Okay? It doesn't have to travel through you anymore. Okay? Because electricity is always going to take this path of least resistance. This is why, have you ever seen, well, you guys might think I'm crazy here, have you ever seen how an electrician might work with one hand behind their back? Okay. Okay. Why is that? Exactly. Okay. Because if we think about something, all right, if I accidentally grab something that has some electric current running through it, if I grab it with both hands, okay, basically I've made a circuit. I've made a circuit that goes up my arm, all right, through my chest, and then down through my other arm. Okay. People die from getting electrocuted because electricity across your heart. Okay. Your body can take a certain amount of electricity, all right? If I have I don't know, even a few amps running through my arm, it's going to hurt, but it's not going to kill me. Okay. But if you have electricity running across your heart, that can stop your heart. Okay. But if I only have one hand, all right, now the easiest path really for that electricity is just to go from one finger to another finger. All right. It'd take a lot more current, a lot more voltage for that electricity to travel all the way up my arm through my chest. It's just a lot easier to go through one hand here. Okay. Good. So enough scary examples. All right. But the point is, electricity is always going to take this path of least resistance. Okay. Now, we also need to spend a decent amount of time talking about how we get electricity. And I know it's a lot of me talking today. You guys will just have to bear with me. Okay. And the way we get electricity is actually from magnets. What do we know about magnets already? Positive and negative, which in a magnet we really just call north and south. Okay, that's easy enough. And so what do we know? If I put two north ends of a magnet together, what's going to happen? There we go. Just like charge, all right, opposites attract, and like repel. And I have another great example of this. Okay, I don't know if everyone in the back can see. Well, I basically have a couple tiny little button magnets here. So if I put them down here, and I push it so that two north ends, all right, I can push one along because they don't want to be near each other. There's a force repelling them. But if I flip that over, okay, now there's this force attracting them, okay? Opposites attract, likes repel. How do I make a magnet? If I have, say, this iron nail here, I could run electricity through it. What else could I do? Now you guys are thinking too complex. I could just attach it to a magnet too, right? You're absolutely right about how we get a permanent magnet. But if I want to make this a magnet just right now, all I have to do is attach another magnet to it. Because what this iron has in it is this iron has a lot of individual magnetic parts. Okay. So what do you think happens when I stick this magnet next to all these tiny magnets? They all line up. Okay. So now I have all these norths that want to be near the south, and all those south parts that want to be near the north. Okay. So I've made a magnet with another magnet. Okay. So now if I take this great demonstration device, take this paper clip, all right, it now sticks to this. Okay. But if I take off this magnet, get it off there, all right, now it's no longer a magnet. Okay. It's only a magnet so long as I have a magnet attached to it. Now the other way you said was with electricity. In the same way, if I wrap a coil of wire around here and I run electricity through there, I can use electricity to create a magnet. Because what we haven't talked about yet is that I can't have electricity without magnetism, and I can't have magnetism without electricity. Is that right? Okay. Because every electric field, all right, so we call this an electric field, an electric wave, all right, every electric field has a corresponding magnetic component. Now I can't draw this very well on the board, okay, but if we think of an electric wave, electric field parallel to the board, it's going to have a magnetic field that's perpendicular to the board. Okay. This electricity moving creates a magnetic field. Magnets moving create an electric field. So we can't have one without the other. Where do we see an example of electricity used to create a magnet? Yeah, like a junkyard, right? Those big cranes they have, all right? They run electricity through there, create a magnet, pick up stuff, then drop it off. Okay. But now, this is useful for junkyards, and this is useful for getting magnets to stick to fridges, but this doesn't really help us in everyday sense. Okay? In everyday sense, I need to figure out how I'm going to use this magnet to create electricity. There you go. See, you've taken more advanced classes about electricity than this. Just a few. Because let's imagine this situation for a while. Okay? Everyone seen a multimeter before? If not, all right, it's just a simple tool, all right, and so yeah, people have them. You just carry around multimeters. That's cool. All right, but basically, if you haven't seen it before, it's just a simple tool to measure different electrical properties, all right? Current, voltage, all right, those things, okay? So right now, I have it set to measuring current. I have it hooked up to just this coil of wire, all right? And as expected, there's no current, all right? Because it's just a coil of wire, all right? So let's see if we can picture this coil of wire. What's that coil of wire made of? Copper, probably. If I look deep enough, what is copper made out of? Copper atoms, right? And we know every atom is made of protons, neutrons, and electrons. Okay? Metals are kind of unique, as we'll see in our chemistry chapter, because it's really easy to get those electrons in metals to move around. Okay? We can think of these electrons as being kind of near the surface. Okay? So these electrons in here are near the surface. If I stick a magnet here, okay, magnet, and I move this magnet up and down, okay, since we just said every magnetic field has an electric field, every magnetic wave has an electric wave, and vice versa, if I move this magnet up and down, basically what I'm going to be doing is creating this electric field, electric wave. I'm actually going to push these electrons around this coil. Okay. And what are moving electrons? What's another name for that? Electricity. Current, right? Current's just that movement of charge, this movement of electrons. Okay. So I can actually do that right here. Okay. Let's see if some people can see this. Okay. So I'm just taking my magnet here, my coil of wire. I'm just going to stick this in my coil here. If I move this up and down a little bit, do I get a current? Yeah. Now it's not much, right? Because this is a pretty small scale. But I do get some current. All right? I don't know how much I get. Well, okay. Maybe 3 microamps. Okay. But this is exactly what's going on in power plants. It doesn't matter if it's coal, nuclear, hydroelectric, all right? It's a little bit more advanced than this. Instead of just a coil and a rod, they actually have a magnet spinning around in a coil, all right? But it's the same thing happening, all right? No matter what. And the name we have for this, we just call this induction. Because you're inducing electricity with a magnet. Okay? Good. Any questions about this? All right. We're almost done with new material, I promise. Okay? What 2 types of current do we have? All right. AC and DC. Okay? DC just stands for direct current. And direct current is really the easiest type of current to understand. Okay? That's the type of current we've been talking about so far. If I make a simple circuit up here, I have a battery here. I'm just going to connect this battery to a light bulb. Okay? What do you know? Light bulb comes on. Shocking, right? Okay? Basically what's happening here is electricity is traveling from one end of this terminal. So electrons are going from one end of this battery through the light bulb down to the other terminal. All right? Simple enough. Why would this not work if we were doing this from a power plant? Where's the closest power plant? One in Westlake, right? Okay. That's maybe 20 miles away, right? So what problems do you think we'd have? Okay. It has problems traveling that far. Because remember, we don't live in a perfect world. Those electrons traveling from that power plant 20 miles away have to travel through 20 miles of copper wiring, through switches, go all the way here, and then travel all the way back. All right? There's a ton of chances for loss. All right? It's horribly, horribly inefficient. But with alternating current, or AC, instead of just having this direct path, okay, we take advantage of the fact that all these wires in this building outside are full of electrons. Instead of pushing all the electrons in one direction, alternating current pushes and pulls these electrons in both directions. So now instead of having to travel all the way from that power plant in Westlake, all these electrons are doing are just moving back and forth along the line. Okay? There's still work being done, all right? That power plant's still important because it has to do that pushing and pulling, but there's a lot less chance for loss. Okay? There's a lot fewer chances for these electrons just to go away. Okay? What else do you think we do to prevent loss? Other way around, right? Because if we have a lot of current, yeah. If we have a lot of current, if we have a lot of moving electrons, there's more chances for loss. So basically what we do at those power plants, ooh, that's not right, okay, is we have a really high voltage, all right? So those power lines out there probably have 20,000 volts running through them, okay? Power lines down by the interstate probably have around 230,000 volts running through them, okay? But the power is always going to be the same. So if I say the power is the same and I jack up the voltage really high, what has to change as well? Yeah, the current goes down. So by having a really high voltage, we can cut down the current a lot, and with less current, there's less chance to lose that energy. Now, anyone know, how do we do that? How do we change the voltage? Yeah, transformer. If we look outside right now, okay, well, maybe now you guys can see this, okay, but if we look outside on that power line right outside, see those 3 cylinders there? Okay, those are just transformers. Okay, they're changing the voltage from the power line into what we need in this house, this room, this building. Okay, the same for houses too, though. Okay, and a transformer is really not a bad, very complicated device. Okay, in the middle of each of those transformers, all right, is this iron core. All right, by changing the amount of times you wrap this wire around your input side and change the amount of times you wrap it on the output, you change the voltage. Okay? So the voltage out of any transformer is just going to be equal to the number, well, if I can write this, the number of coils going out divided by the number of coils going in, all multiplied by that input voltage. Okay. And we can rewrite this a little simpler. And we just say 2 is going to be our output. V2 is equal to N2 over N1 V1. In the input. So the voltage coming out here is dependent on the voltage coming in and this ratio of the number of coils going out and the number of coils coming in. So in this case, let's say we connected a 9-volt battery to this transformer. Okay. It looks like there's about 5 coils over here and maybe 10 over here. Okay. So our voltage coming out of this situation would just be 10 divided by 5 times that 9 volts. So just 2 times 9 volts, or 18 volts. So here, since we had more coils, since we had more times wrapped around this output, we increased our voltage. And so this is an example of a step-up transformer. step up because we increased our voltage because we have more coils on the output. Yeah.
I was watching on TV. There's like this place in Alaska. I forgot what it's called. I think it starts with an N. But it's like a bunch of like towers that have like electricity or something, and like beams into space. And they said like it can like affect weather and stuff.
Well, yeah, because if you think about any of this electricity, right, all this is, you're talking about a lot of power, okay? Because what's the most common reason for a power outage around here? Weather. That makes a transformer blow, right? Okay? So since we have so much power run through, these things blow up all the time, okay? At the same way, all right, if we talk about moving this wirelessly, the reason we don't do that more often is because you dissipate so much energy, okay? So by even shooting that up in the air, all right, you do lose so much energy. But that energy goes somewhere. The energy goes to the surrounding air, okay? This is why people are afraid to live under power lines, okay, because they're worried about the electric waves and everything like that, okay?
Is that strong to affect you?
Not conclusively, all right? If like we live under a power line like this, there's probably nothing wrong there, okay? Because they are not extremely well shielded, but at the same time, it's only 20,000 volts, okay? But if you go out to those huge ones with the 230,000 volts running through there, yeah, there's a lot more energy running through there. So if you do live under one of those, it could potentially be harmful. Because remember, all this energy has to go somewhere, and that's why we say we never X-ray an unborn baby, because it's too much energy, all right? It's the same way, all right? You probably don't want to be exposed to that for too long. Okay? And it's the same way. Have you ever, well, this is getting a little off topic, okay? But you know that they store like nuclear waste in basically big pools of water, okay? Yeah, because they do generate a certain amount of heat. But at the same time, all right, if you go swimming in one of those pools of water, well, no one's going to let you do that, all right? But at the same time, that's not going to hurt you, all right? You could swim all day in one of those pools filled with radioactive waste, okay? Because that water absorbs so much of that energy, all right, that you'd be fine, okay? So really for these power lines, right now, I mean, sure, all right, if we went and touched one of those power lines, we'd die real quick, okay? But at the same time, we're far enough away, there's so much air between us that we're never really going to get hurt. Another off topic, you ever seen that Mythbusters where they see how far underwater you have to dive before you can escape someone shooting at you? Yeah. It's the same way, all right? When we think about something like that, if you have something to dissipate that energy, all right, obviously water's a lot better, all right, than air. But at the same time, all right, as long as the energy goes somewhere, you'll be fine. Okay, let's try another one of these. Okay. Because remember, just like everything we've seen so far, the hardest part is going to be identify what you know and what you don't know. Okay. So let's say we are talking about one of the bigger power lines out here. We'll say it's 100,000 volts. Okay. And the output on this side is 20,000 volts. So we're going from a medium range power line to a one that we'd see right around here. Okay. In this case, I'm going to say we start off by wrapping this around 200 times. And I want to know how many times do I need to wrap around here to go from 100,000 to 20,000, sorry. Why don't you guys take a minute and try this one. I'll put this up here. V2 equals N2 over N1 times V1. So see if you can identify each of those parts and see how many times you need to wrap that around. Okay, we'll take a minute. Help your neighbor if you were too quick. That's how many times this is wrapped around here, sorry. So we're wrapping around here 200 times. And I want to know how many times we wrap around this side to go from 100,000 to 20,000. We're getting a little stuck with this? Well, why don't we identify what we know, all right? So this is 100,000 volts in. So which variable is this? This is V1. Okay, so this is our input. Okay, so we start with V1. Okay, and so that means also that this 200 is going to be what then? In1. Okay, so everything on the left here, this is all my input. And all my input's going to be 1. So that means on my output here, this 20,000 is going to be V2. So what I don't know here is into. But once I have those parts identified, then I can just plug it into my equation, right? I can say, well, V2 is 20,000. Okay, into I don't know, but I know in1 is 200. And I know my input voltage is 100,000. So if I start canceling out zeros here, there's 2 zeros, there's 2 zeros. So I have 1,000 divided by 2. So N2 times 500 should equal 20,000. And now if I divide both sides by 500, I get that N2 is equal to 40. So this is kind of the reverse of the last one. Here, since we went to a high voltage to a low voltage, it's what we call step down. Okay. And the other thing we can notice here too, okay, is that we went from a high voltage to a low voltage. We went to a high number of coils to a lower number of coils. So if we decrease the amount of coils, we decrease the voltage. If I flip back here for a second real quick, if I increase the amount of coils, I increase the voltage. How are we doing with this? Sure. Why don't you guys try one more? Okay. Let's try, this one will be a little simpler. Let's say we start with 2 coils over here. Okay. We end with, well, I need another coil there. We end with 3 coils. Okay. If my output here is 9 volts, what's my input voltage? Oops. What are you doing right away? Is that voltage going to be higher or lower? Lower, right? Because on the left, on that input, you have less turns than on the right. So your voltage should be lower. Where we have a test on Wednesday. So what did you guys get here? 6. Good. And if we notice here, even before I'll put this up here real quick. But we notice this ratio here of voltage is the same as this ratio of the coils. With a lower number of coils, it's easier to see, all right? 2 to 3 is the same as 6 to 9. So if we plug this in, all right, here we knew our output voltage. Okay, we knew 3 over 2 times V1. So 3 over 2, that's just 1.5 times V1. So if we divide both sides by 1.5, we get that our V1 is 6 volts. Okay. So that's all we have to talk about for this part. Means we have a little less than a half hour for a review. So any questions before we move on to the review? All right. So now what I've done for the review, okay, is later this afternoon, I'm going to put this same review on Joule that we had for the first test. Okay. This just goes through each of those different chapters. Okay. Remember, it's going to be on work and energy, heat, waves, and electricity. Okay. Goes through each of those chapters, discusses the individual subtopics for each of them. Okay. And then has the corresponding homework problems. Okay. Now these homework problems are just the same homework problems I assigned throughout the previous lectures. Okay. But at the same time, if you know, looking at this list right now, that, hey, I have a problem with temperature, go back and do these a couple more, okay? Because these will go along with that. And remember, this will all be on Joule, so you can print this out. Have it. Not yet, all right? Give me a couple hours, all right? This afternoon it'll be up there, okay? But what is already on Joule, okay, are all the class notes that we've talked about, okay? Besides electricity, which I'll post later today. Okay, so there's work and energy class notes, heat, all right, and waves. Okay. In addition, what I've started doing, why I'm wearing this weird thing right now, okay, is that I've started recording all of our lectures too. Now we don't have a ton of our lectures here, okay, but if you click on this link here, basically this has our most recent lecture about circuits and magnets. It also has everything we'll do today, along with probably a more detailed review. Okay, and so really all this is, I know you guys just love the chance to listen to my lectures. So far we've learned, okay, all right, but this is basically just capturing everything I'm writing up here today, all right, along with my voice. That sounds weird to yourself, all right? So you can just see everything we did. Now I don't expect you to, watch each of these, all right, all the time. But at the same time, if you do want a little review, if you didn't miss anything I'm saying today, all right, you can go back and watch this. Okay. So that's all that's on Joule. Now let's go over these review topics. Okay, obviously we only have 25 minutes now, so I'm not going to be able to work out all these, all right? But we can go through them kind of quickly. Okay, let's start with work and energy. Okay, what do we define work to be? Oh, okay. Remember, we said work was force times distance. Okay. This was kind of our next step, okay? I can apply a force to something like this wall, and even though it's not moving, I'm applying a force, all right? But work says I have to have both a force and a distance. So if I have some guy, all right, who's pushing a box with a force of 10 newtons, if that box isn't going anywhere, how much work is he doing? None at all, okay? But if that box moves 5 meters, okay, then I can use my equation here and say, well, work is just equal to that 10 newtons times 5 meters, 50 newton meters. And what's a newton meter? A joule, all right? So 50 joules worth of work, okay? And remember, joules was our unit for everything we did in this chapter, okay? Because we also talked about kinetic energy and potential energy. What's another one word to describe kinetic energy? Energy in motion, okay? Yeah, that's what kinetic means, basically movement. What about potential energy? Stored energy. Okay? And once again, we had equations for both of these, all right? Remember kinetic energy, EK, was just 1/2 mv squared. So the more mass you have, the faster you're moving, the more kinetic energy you have. Potential energy, we said, can be caused by a lot of things. But when we think about potential energy due to gravity, that's where we get my favorite equation here. EP is equal to mad. Okay? So the more mass the object has, the higher above ground, the more potential energy it has. Okay. Now the other important thing we said, we talked about the conservation of energy. What does it mean when I say energy is conserved? It's not created or destroyed. Okay? What this means for us is that if I start, let's say, a 5-kilogram bowling ball sitting on top of a 3-meter desk, how much potential energy does that bowling ball have? How would I figure that out? What? Times 9.8. Yeah, because that mad, remember, is just my mass times acceleration due to gravity, which is 9.8 meters a second squared, times my distance above ground of 3 meters. So when I multiply all that together, I get about 150 kilogram meters squared over second squared, which is the same thing as 150 joules. Okay? How much kinetic energy does that bowling ball have that's just sitting there? Zero. Okay? If something's not moving, it does not have any kinetic energy. Okay? Now let's say this bowling ball falls. It falls here, and now it's 1 meter above ground. If I do this all again, I'm going to get that my potential energy is equal to 50 joules. Where did those other 100 joules of energy go? Kinetic. Good. Okay, so it's all kinetic. Okay. So remember, at each spot along here, there's going to be 150 joules of total energy. At the very bottom, I'm going to lose all this potential energy, and it's all going to be kinetic. Okay. At the very top, it's all potential and no kinetic. But conservation means that that total energy is not going to change. Good. All right. Let's keep going then. Quicker than I thought. Okay. The last thing we did in this chapter was we talked about power. Okay. And remember, power, we said, was just one more step to deal with work. Okay. Power is just equal to work over time. Okay. So it's not just how much work we did, but how fast we did it. So if I go back to that example, that guy applying 10 newtons of force, moving that box 5 meters. So we know his work was just 10 newtons times 5 meters. But if I took this one more step and said it took this person 20 seconds to do this, his power would just be that 50 newton meters divided by 20 seconds, or 50 over 20 newton meter over second, or 2.5 joules a second. What's a joule a second? Watt. Okay? So 2.5 watts. And remember, this watts is the same thing that we saw before. Okay? Same thing for electricity, same thing when we're talking about pushing boxes around.
So power is going to be watts and work is going to be joules.
Yes, power's always watts, work is joules, kinetic energy is joules, potential energy is joules. Okay? Basically, energy is joules. Okay. I know we're moving kind of fast, but stop me if you want to see anything in more detail. Okay? Let's move on to heat. Okay? First thing we talked about with heat was we talked about temperature. Temperature, we said, was the average kinetic energy. Okay? So, like I asked on that quiz, what's moving in that wall over there? And you better know this for the test, too. The atoms and molecules. Okay? So we didn't do too good on the quiz with that. Okay? But even if that wall isn't moving on its own, okay, the atoms and molecules in that wall are moving. And that's what we talk about when we talk about temperature. Okay? Now, we did have a couple equations with temperature. We said, okay, the temperature in Fahrenheit is equal to 1.8 times the temperature in Celsius plus 32. And then we said the temperature in Kelvin is equal to temperature in Celsius plus 273. Okay? But really, these are just plugging in what we know. Okay? Because any of these temperature scales, whether it's Fahrenheit, Celsius, or Kelvin, are all just ways to measure temperature. Okay? They're all saying the same thing. So when I say something is 32 degrees Fahrenheit, 0 degrees Celsius, or 273 Kelvin, all those are saying the same thing, just in different ways. Just like saying that table is 2 meters long is the same thing as saying it's 200 centimeters long, which is the same thing as saying it's almost 2 yards long. Okay? Just different scales. Now, we also talked about heat, and we said heat, all right, was a form of energy. Okay? Why did I talk about donuts when I was talking about heat? Because it has some amount of energy in it. Most of the time, we use that energy to eat, to walk around, to live, whatever. Okay? But at the same time, like we saw in the lab with those Cheetos and marshmallows, if I lit this donut on fire, it would release that energy in heat. Okay? And remember, the only tricky thing about this is that if this donut says it has 100 calories on its label, they're actually food calories. Okay? So 100 food calories is actually 100,000 calories. Okay? And once again, all right, 1 calorie is equal to 4.2 joules. So if I set up this unit conversion, if I want to know how many joules are in this, put what I want to get rid of on the bottom, so calories, what I want to keep on the top, joules, and then all that's equal to 420,000 joules. Okay? So remember, that seems a lot more imposing now. Okay? Good. Now remember, we also talked about specific heat. Remember, that was another equation. We said H equals mc delta T. But that's all well and good, but can you tell me what specific heat is in a word? What does it mean when two things have a different specific heat? Not in a word, a sentence. Kinda. Remember, specific heat, we said different materials absorb heat differently. Okay? This metal feels colder than the wood up top because it absorbs heat differently. Okay? So we said water was our example here. Water has a specific heat of 1 kilocalorie per kilogram degrees C. This means that it takes 1 kilocalorie of heat, 1 kilocalorie of energy to change temperature of 1 kilogram of water by 1 degree Celsius. Okay? But other things are different. All right? That metal is a lot lower. That means it takes less heat to change the temperature of metal than it does water. Okay? Both things can have heat added to them, but they're going to change temperature differently. This is the same reason we said if you go to the beach on a hot spring day, that sand's going to burn your feet, but the water might be cool. Both are being exposed to the exact same heat, but that sand absorbs the heat a lot quicker than that water. The sand absorbs the heat, changes its temperature a lot quicker than the water does. Okay? And that's what we mean by specific heat. And don't worry, all these specific heat values for water, sand, everything will be on the test. So you don't need to memorize this. We only need to know that specific heat is C.
You don't need to know that specific heat is C?
You just need to know that specific heat is C. Okay? You don't need to memorize what all the different values
Like
are.
mass times specific heat change
Yeah.
is what? Temperature?
Temperature, yeah. Okay. Okay. Oh, and then the last thing we talked about when we talked about heat, we talked about how do we transfer heat. Okay. Remember there were 3 different methods. What were those 3 different methods we transfer heat?
Conduction, convection, and radiation.
There we go. Conduction, convection, and radiation. Okay? So this is how we get heat from one thing to another. And really what you need to be able to do here is be able to give me an example of this. Or if I give you an example, you need to be able to tell me which one of these it is. So if I think about the air conditioning in your home, which one is that? Convection. Okay? Because remember, in convection, we're going to heat, or in this case, cool down a small pocket, and then we're going to blow that cold or hot air around. Okay? And that's how we're transferring heat. What's a good example of conduction? A stove. Okay? Stove's probably the best example. A stovetop, all right, you put a pan in direct contact with that hot stovetop, that heat flows through direct contact. Okay? And finally, what's an example of radiation? Sun. What's another one? Microwave. Okay? Remember, radiation is just heat transfer through light. Okay? Good. And so that's all for that heat chapter. That's good because we're running out of time. Okay? Finally, let's get to the waves. Okay? Waves, I was really surprised that everyone did not do as well as I thought on this last test or this last quiz. Okay? Because really, there's a lot of memorization in waves, and maybe that's what you weren't expecting so much. Okay? There's a lot of concepts here. But remember, one thing all waves have in common, okay, is they all have a few basic properties. So this is something we need to know. Okay? The wavelength is how long a wave is. Okay? The period, measured with a capital T, is how long it takes for that wave to pass by. And then finally, the intensity, or how big a wave is this amplitude. Okay? So you need to be able to tell me things like, okay, if I start shouting at you, which one of these changes? No. The amplitude would change. The amplitude describes the intensity of the sound wave. Okay? But at the same time, what if, I don't know, instead of being white light, these lights suddenly change to blue? What would change there? Frequency would change. What else? Yeah, the frequency and period would change as well as the wavelength. Okay? Good. And remember, we didn't put frequency on here, but frequency is just 1 over the period. Okay? So remember, frequency says how many waves pass in a second, and period says how long it takes for one wave to pass by. So they're both saying the same thing, just in slightly different ways. Okay? Good. Remember, the other thing we also said is all waves are traveling. So the velocity of a wave is equal to its wavelength times frequency. Now, some waves travel faster than others, right? Okay. What travels faster, light or sound? Light. How do we know that? What's a good example? Lightning. Okay. We see lightning before we hear it. And I'll put this on the test. I'll say the velocity of light, that's probably exactly how I'll put it on the test, v light equals 3 times 10 to the 8th meters a second. So anything that's light, okay, travels at 3 times 10 to the 8th meters a second. While anything that's sound travels at around 344 meters a second in air. Okay. But this means if I give you a question like this, you'll have to know if it's light or sound. If I'm talking about radio waves, are radio waves light waves or sound waves? Light. Okay. Remember, radio waves are light waves that carry sound information, but radio waves travel at this 3 times 10 to the 8th meters a second. Okay. If I, on a tangent here, If I pull up to your car at a stoplight, okay, and I have my music blaring as loud as it can, and you roll up your windows, what are you more likely to hear? What type of sound? Bass. Why? It's got a lower frequency. Lower frequency, which means it has a longer wavelength. Remember, those longer wavelengths can more easily pass through things. Okay, remember that example we did in class of me with that wave and someone throwing something at me? Okay. Yeah. Well, in reality, if we have a nice long wave, all right, it's easy for that wave to pass through something without getting hit. Okay. It's easier for something to go right past that wave without anything happening. But if we're moving that wave up and down really quickly, then that wave is more likely to hit something. Okay. And that finally brings us to our most recent chapter about electricity. Okay. Remember, once again, we have a bunch of definitions here. Okay. Because remember, we said electric charge. What do we know about electric charge? Nothing. We know nothing about electric charge. All right, that's good to know. If I have a positive charge and a positive charge and I put them close together, what's going to happen? They're going to repel, right? Because just like we were just talking about magnets, okay, like charges repel. Okay? And that must mean that opposite charges attract. And remember also, when we're talking about these like charges and unlike charges, all these charges really only come from two places. Either electrons with their negative charge or protons with their positive charge. Okay? So when I say something has an electric charge or is negatively charged, it means it has an excess of these electrons. So the positively charged has an excess of protons. Because in us right now, there's all sorts of electrons and protons. But for the most part, they're balanced. Okay? It's only when they get unbalanced that we notice this. Okay? And we also started talking about things like current. How would you describe current to me? Charge in motion, okay? The flow of charge, the flow of electrons, okay? It's charge over time, all right? Because our equation we had for that, and you're absolutely right, all right? Current is equal to charge over time. Okay? It's how much charge moves in a given amount of time. Okay? Why do charges move? What do we need to have in order to have current? How do we get electricity, though? Not just current, we also need voltage. We need voltage. Okay, voltage is the reason we have charge moving. All right, we have to do something to separate those charges to begin with to make them want to come back together. Okay, and that's where voltage comes into play. All right, and then remember we ended last week with Ohm's law, okay, and the power law. Okay. So just remember, if we know any two of these, we can get the other two. Voltage equals current times resistance. Okay, power equals current times voltage. And remember, the only thing to be careful of, which I might be a little tricky, all right, is that this is voltage measured in volts, current measured in amps, resistance measured in ohms. So if I give you something like, I don't know, 3 kilovolts, okay, and 2 mega ohms, probably won't give you mega because we don't need to memorize mega, but you'll have to convert them first.
So say that one more time, voltage is measured in?
Voltage is measured in volts, current's measured in amps, resistance is measured in ohms. Okay, and so power is measured in watts, then current in amps, and voltage in volts. Okay. Good, good.